and special right triangles, also to solve real-life problems involving special right triangles. Our essential question: what is the relationship among the side lengths of a 45-45-90 and a 30-60-90 triangle? So let's start with a square. We know that a square, when it's cut by a diagonal, will divide the angles into congruent angles. It also divides the square into two congruent triangles that are isosceles. So that makes these angles 45-degree angles. This takes us into our 45-45-90 triangle theorem. In a 45-45-90 triangle, the hypotenuse is always square root of 2 times as long as each leg. Here's our picture. So whatever the leg length is, the hypotenuse can be multiplied, you can multiply the leg length, whatever it is, times square root of 2. Also, you can go from hypotenuse to leg by dividing square root of 2. So our ratio is always the 45-45-90, smallest angle to largest angle, and then our ratio of our sides is x to x to x square root of 2. And these are labels that you can easily put on your 45-45 special right triangle in order to help you solve for any side length. So this is our very, very, very important equation that we can set up every time we're trying to solve for one of the side lengths. No matter what side length you're looking for, this equation works. What makes this a special right triangle is the base angles are equal, so they must each be 45 degrees. All right, so let's start by looking at a couple of examples. We're going to find the value of x and write our answers in simplest form. So since we're dealing with 45-45 right triangles, we'll start by setting up our equation. So hypotenuse equals the leg times the square root of 2. And next you'll just substitute in the values. So our hypotenuse is x, and then our leg is 8. So we end up plugging in 8 for the leg, and we get 8 square root of 2. So the length of your hypotenuse is 8 square root of 2. So when it says write your answers in simplest form, this would be a simplified radical. And this would be the exact value, no decimals. All right, example 1b. Again, it's a right triangle, so we use our special equation, and then we substitute. So we get 5 square root of 2 in place of the hypotenuse, and then we have x in place of the leg, and it's always times square root of 2. So in order to solve for x, we've got to divide square root of 2 on both sides. And what we see over here is that the square root of 2's will divide each other out to be 1. No more square root of 2's. That leaves us with a length of our leg is 5. Here's some extra examples that we can look at as well. Again, we're dealing with 45-45 right triangle. And we know that because each of these legs are the same length, so that makes it isosceles. Since it's an isosceles right triangle, then we are dealing with 45-45-90 right triangle. So we start with our equation, hypotenuse equals leg times square root of 2. Substitute what we know. So we know that hypotenuse is m. We know that the leg is 3 square root of 2, and then it's always times square root of 2. Remember, any radical times itself is the same as saying that square root of 2 squared. And squareds and square roots undo each other, so that's why we have just the 2 outside the radical and no more squared. So then we have 3 times 2, which is 6. So the length of the hypotenuse is 6. Our next example is a square with a diagonal length of 8. We know it's a square because all sides have the exact same label, and we see the right angle symbol in the corner. So we are dealing with a 45-45 right triangle. So we use our hypotenuse equals leg times square root of 2. We substitute 8 for the hypotenuse, x for the leg, and it's always times square root of 2. So we're trying to solve for x, so we need to divide square root of 2 on both sides. You can never leave a radical in the denominator, so we have to multiply times square root of 2 in the numerator, in the denominator and in the numerator. This will take care of no more radical, so you have 2 in the denominator, and then 8 times square root of 2 in the numerator. And since the 8's on the outside and 2's on the outside of a radical, they can be simplified, so 8 divided by 2 becomes 4. So the length of your leg is 4 square root of 2. All right, next we have our second special right triangle, which is the 30, 60, 90. Triangle theorem states that in a 30, 60, 90 triangle, the hypotenuse is twice as long as the shortest leg, and the longer leg is square root of 3 times as long as the shorter leg. So let's take a look at our picture. So the smallest angle is 30, and it's directly across from the shortest leg, which we'll label X. Your hypotenuse is always the longest side, and it's across from the right angle. And it is twice the length of the shortest leg. Always, always. And then your longer leg is exactly square root of 3 times as long as the shortest leg. So everything's in relationship to that shorter leg. So here's your smallest angle, largest angle, shortest side, longest side. So our ratio goes from 30 to 60 to 90, and the side lengths ratio is X to X square root of 3 to 2X. So here's two equations that we can set up when we're dealing with a 30, 60. You can say an hypotenuse is equal to the shorter leg times 2, and the longer leg is equal to the shorter leg times square root of 3. Now just to help you get better acquainted, here's some images to kind of help you with identifying your shortest leg, your longest leg, and your hypotenuse. And just knowing that the order of the angles corresponding to the order of the side lengths. And what's most important is that you're always looking for that 30-degree angle first. Once you have that 30-degree angle, all the other angles kind of fall into place. And using these labels will help us solve for unknown lengths. All right, let's look at our first example for the 30, 60. It's find the value of n and m, write your answer in simplest form. So we are dealing with the 30, 60. So let's start by taking a look at our formula. So we'll start by looking for m, and m is across from your shortest angle. And we know that because our other angle labeled 60, so we are across from the 30, which is m. So we know that the relationship is that the longer leg is going to be equal to the shorter leg times square root of 3. So you substitute 9 for the longer leg, m for the shorter leg, and it's always times square root of 3. So now we need to solve for m, so we're going to divide square root of 3 on both sides. Again, you cannot leave radicals in the denominator. So you've got to multiply both the denominator and the numerator by the same radical. Any radical times itself will undo the radical. So we have just 3 on the outside of the radical in the denominator, and then 9 times square root of 3 in the numerator. And then the 9 and the 3 will divide with each other to become 3 over 1, which is simply 3 times square root of 3. All right, next let's take a look at finding n. So here to find n, we know that the hypotenuse is always equal to twice the length of the shorter leg. So we substitute n for hypotenuse, and then 2 is times m, the shorter leg. We just figured out m, which is 3 square root of 3, so we're going to substitute 3 square root of 3 in place of m. And here we have a 2 times a 3, and we want to multiply those together. They're both on the outside of the radical, so they can get multiplied together. The 3 is on the inside of the radical, and therefore cannot be multiplied by any number on the outside. So the length of the shortest leg, for the hypotenuse, is 6 square root of 3. All right, here's an extra example where you can find the value of c and d. Always write in simplest form. So again, the same formulas. It's going to be important that you always identify your shortest side length by looking for the smallest angle. Our smallest angle is not labeled, but I have the label of 60 degrees and the right angle, so this must be my 30-degree angle. So there's my shortest length, or shortest side. So use your two special formulas and substitute and solve for the unknown. And for the length of C, we get 4 times the square root of 5. And that's because when you substitute in and you divide both sides by 2, this 8 in the numerator will divide with 2 in the denominator to become a 4. Nothing happens to the radical. On the second setup for finding the longer leg, you've got longer leg equal to the short leg times square root of 3. So we already know the shortest leg is 4 square root of 5. So then multiply it by square root of 3. And we have 2 different radicals, which can be multiplied under the same radical to become 15. So we have 4 square root of 15 for the length of the longer leg. All right, for this next example, we're trying to find the altitude of the equilateral triangle. Since this is an equilateral triangle, we know that all 3 angles of the larger triangle are going to be 60 degrees. So that means our altitude, labeled A here, is going to cut this angle here. It's going to be a bisector into 2 equal angles of 30 degrees. So we have 2 30-60 right triangles. The length of our hypotenuse is 2x. So that makes the label over on this entire side also 2x since it's an equilateral. So all 3 sides of the original triangle are equal. And if we look at each side, since we have 2 30-60s, that makes it a length of x from here to here. And then the same length x over here, getting us a total of 2x. So we can always use Pythagorean theorem for all right triangles, whether they're special or not. So let's set up our a squared plus b squared equals c squared. Substitute in a for one of your legs and x for the other leg and 2x for the hypotenuse. Simplify, so the 2x can become 4x squared. Combine the x squareds together, so subtract the x squared from this side to join with the 4x squared to become 3x squared equals a squared. And then square root both sides, so that undoes the squareds. So on the left side we have a outside of the radical and no more squared. On the right side, the square root and the squared on the x are the only ones that undo each other. The 3 doesn't have a power 2 on it. Therefore, it stays under the radical. So it will not get out from under the radical. It does not have a power 2. So only this power 2 on the x and this square root undo each other. It does not undo on the 3. So your final answer for the altitude is x squared root of 3. All right, let's pause our video here and try all of these examples on your own, and then unpause to reveal your answers. I say if a cat can do it, you can do it too. Grab those calculators and start calculating. All right, here are your answers, so check to see if you got them right. If you did not, definitely bring in your work and clarifying questions and we can go over it in class. All right, let's take a look at our first of 2 real-world situations. We've got a road sign shaped like an equilateral triangle. Estimate the area of the sign by finding the area of the equilateral triangle. So we're going to need to split this triangle into 2 congruent 30-60 right triangles, which we've already seen in a previous example. So your sketch should look something like this, where h represents your height or altitude. You've got your 2 angles 60s marked, which means your other angle 30 would be split at the bottom here. So you have 2 special right triangles, 30-60s. So we're going to be using our longer leg equals short leg times square root of 3 formula, and then substitute. So h represents your longer leg, the shorter leg is 18, and then that's times square root of 3. So in order to find the area, we need the base times the height times 1/2. So we substitute 36 for the base, because our base of our triangle is this full length, 36. And then we just figured out the height with our special formula, so 18 times square root of 3. Type that all in the calculator and round it off, so approximately 561.184. So the area of the sign is about 561 square inches.